Good afternoon, sir. My name is Uday Aditya Burwa, and I'm going to present my answers for the sessional test 2. Starting with this first question, considering consider air entering a heated duct at P1 is equal to 180 m and T1 is equal to 288 Kelvin. Ignore the effect of friction. Calculate the amount of heat per unit mass in joule per kg. Necessary to choke the flow at the exit of the duct as well as the pressure and temperature at the duct exit. For an inlet, Mach number of A is equal to M1 uh, of A. M1 is equal to 2.0, which is a supersonic flow, and B, M1 is equal to 0.2, which is a subsonic flow. Now, according to the question, the flow is a Rayleigh flow as uh, duct is heated. As a result, air entering the duct will also get heat up. Suppose if you consider a duct with point 1 and 2 as the extreme endpoints on both sides, like point 1 at the initial part of the duct and point 2 at the end part of the duct. We know upon choking M is equal to 1, that is the sonic condition, and its property at M1 and its M equal to 1 is denoted by P star reference and T star reference conditions. For A, M1 is equal to 2.0. From table A1 we have T temperature at stagnation temperature at point 1 by T1 is equal to 1.8, which gives stagnation temperature at 1 is equal to 1.8 and 288, where 288 is the given temperature at point 1, which is equal to 518.4 Kelvin. Now from table A3, since the flow is in 1D with heat addition, which is a Rayleigh flow, so from table A3, if I just scroll down, table A3 is the one-dimensional flow with heat addition. So just a moment. So from table A3 we have P by P star and 0. Which is equal to 0.3626, and T by T star which is equal to 0.52, and stagnation temperature by stagnation temperature T and by stagnation temperature star reference is equal to 0.7934. So we find out P star, which gives us P star is equal to 2.750 bar, and T star is equal to 544.4.5 Kelvin. Now we can say, I mean, according to the question, we can say that stagnation temperature at point 2 is equal to stagnation temperature at sonic condition. This term means the conditions at sonic state, which is M Mach number is equal to 1, is equal to is we can say this because for the duct which has only 2 points, the initial point, the starting point, where we consider Mach number 1 at the initial stage, at the initial part of the duct, and M2 at the end part of the duct. So the stagnation temperature at the end of the duct will be equal to the stagnation temperature at the reference stage, since the question itself says the uh, uh, choking the flow at the exit of the duct, and since the exit of the duct is represented by point 2, so stagnation temperature at point 2 is equal to stagnation temperature at star reference state, which gives us 653.4 Kelvin. Now coming to the main part of the questions, which was to calculate the amount of heat per unit mass, that is small q, is equal to Cp, which is specific heat at constant pressure, uh, into stagnation temperature at point 2 minus stagnation temperature at point 1. This is actually the formula for uh, a perfect gas. If we consider the fluid air as a perfect gas, and since air is considered as a perfect gas, we get this formula for amount of heat per unit mass, which is equal to Cp into stagnation temperature star reference state. Since we already know that stagnation temperature at point 2 is equal to stagnation temperature star references minus stagnation temperature at point 1, uh, Cp is equal to gamma r, where r is the gas constant, I mean specific gas constant divided by gamma minus 1. For air, we know gamma is equal to 1.4 into 287, which is a value of characteristic gas constant r, divided by 1.4 minus 1, which is 0.47, is equal to 1004.5 joule per kg Kelvin. Finally, q, uh, in the in this equation, putting the respective values of the Cp, this T and this T, we get 1135607.5 joule per kg for M1 is equal to 2.0. Now coming to the second part of the question, M1 is equal to 0.2. In the same way which we did for uh, A, part A of the question from table A1, we follow the same stages to find out stagnation temperature at point 1, which gives 290.3 Kelvin, and from table A3, which is the Rayleigh flow table, we extract P by P star reference, T by T star reference, and stagnation temperature T, and stagnation temperature star reference state, followed by P P star reference, which gives equal to 0.440 bar, and T star is equal to 1394 Kelvin. And finally, to calculate Q in the same way we did for A, we find out the stagnation temperature at point 2, which is equal to stagnation temperature star references, which gives 1672 Kelvin. And finally putting the respective values of Cp, stagnation temperature 2 at point 2, stagnation temperature at point 1, which gives Q is equal to amount of heat per unit mass is equal to 1388154 joule per kg for M1 is equal to 0.2. Moving on to the next question. Conditions before a normal shock are M1 is equal to 2.5, stagnation pressure at 1 is equal to 67 psi, and stagnation temperature at point 1 is equal to 700 degree Rankine. This is followed by a length of Fanno flow. This is followed in the diagram. This is followed by a length of Fanno flow and a converging nozzle. This part, as shown in figure P2. The area change is such that the system is choked. The area change up to here, the area is constant. The area system is such that the system is choked. It is also known that P4 is equal to PMB and is equal to 14.7 psi. To draw a TS diagram to find the M2, M3 and 4F del X by D. Now given conditions are M1 stagnation pressure at 1, which is equal to 4.61949 bar or 67 psi. As we know 1 psi A is equal to 0.0689476 bar, and stagnation temperature at point 8.1 is equal to 388.89 Kelvin for 700 degree Rankine, since 1 degree Rankine is equal to 5 by 9 Kelvin, and other given conditions are P4 is equal to 1.013 bar, which is equal to 14.7 psi. Moving on, uh, now coming to the first part of the question, TS diagram for the system. As you know, the Fanno curve, this is the Fanno curve in the TS diagram. Now, as the question says, a normal shock is followed after M1 to 2.5, which 0.1 travels to 2 with a normal shock. So now the normal shock, which is a wavy curve, is a straight wavy curve in the TS diagram for a Fanno flow curve. As you can see, 0.1 travels to 0.2 through a normal shock. This is the direction of the normal shock. So, and the Fanno curve is divided into two regions. The lower part of the Fanno curve is for Mach number greater than 1 for a supersonic flow, and the upper part is subsonic flow. This part, the dotted line, represents the sonic state, which means the Mach number is equal to 1, divides the Fanno curve into two parts, subsequently supersonic and subsonic. Now, this is the stagnation temperatures for the system, and the stagnation temperature at point 1 and point 2 are the same, will be the same for a Fanno curve, and similarly stagnation temperature for point 3 are equal. This means stagnation temperature at point 1, point 2 and point 3 all are equal. This curve is for the pressure at point 2. These are isobars P2, P3 and P1. Pressure at point 1, the Fanno curve at point 1 is more steeper. This means the slope of the Fanno curve at point 1 is more than the isobar at point 1. So the slope of the isobar of point 1 is less than the slope of the Fanno curve at point 1. Similarly, this will be the stagnation pressure of point 2, and this is the curve isobar for stagnation pressure at point 3, and this is the point 4. Now coming to the second part of the question, from table A2 for M1 is equal to 2.5, we get M2 is equal to 0.513. Now we choose table A2, that's because table A2 is for the normal shock properties, and since M1 travels uh, across a normal shock to flow through the duct, so for M1 is equal to 2.5, we get M2 is equal to 0.53, followed by the stagnation pressure at point 2 and point 1, which is equal to 0.49990. And from table A1 for M2, since got the value of M2 from A2. By interpolation, we get stagnation pressure 2 by T2 is equal to 1.052, and stagnation pressure T at point 2 by pressure 2 is equal to 1.1964. Now from table A4, for M2 is equal to 0.513. Now this table A4 is for the Fanno flow. Now since as the question mentions that air after the normal shock passes through a duct with friction between the fluid and the surface of the walls, which is actually the Fanno flow, characteristic of Fanno flow. And this goes up to this part as the Fanno flow is only for the constant area part. So the Fanno flow would be from this to this. So for mm, ah, so we extract the value of T2 by T star, which is equal to this, P2 by P star, this, stagnation pressure at point 2 by stagnation pressure at star reference is equal to 1.315. And since as already mentioned that stagnation pressures of point 1 and point 2 and point 3 are all same, this is the constant line for stagnation temperature. So we get the value as 388.89 Kelvin. Now P2 by cross multiplication we get P2 by P naught. Since we already have these values, P2 by stagnation pressure at 2, which which is equal to this, and this we got from this, and multiplied by stagnation pressure uh, at point 1, we get P2 is equal to 1.92651 bar. Now since stagnation now since this since we have this, so we can calculate P naught 2 for this from that formula. P naught 2 by P2 is equal to 1.1964. We can calculate P naught 2 since we already have the value of P2. We get P naught 2 is equal to 2.3048 bar. And also we have from the Fanno flow table, P2 by P star is equal to this. So we get P star is equal to 0.92527 bar. Now for M3, this formula is for star reference state for isentropic conditions. Now this formula is independent of any Mach number. Since left hand side of this equation is not a function of Mach number, so we can use this to get to achieve the value of stagnation pressure at point 3. Since to calculate M3 we have to have the properties for M3 like T3, T03 or P03 or P3. So we calculate P03, putting the values we get P03 is equal to 1.75133 bar. And from now for a Fanno flow we have the formula for the fraction between stagnation pressure at point 3 and stagnation pressure at point 2. We have the formula M2 by M3, which is equal to this, to the power gamma plus 1 to gamma minus 1. Since the fluid flowing through the duct is air, so we can use gamma is equal to 1.4. which gives us the power term equal to 3. So mm, since we already have the value of p naught 3 1.75 and p naught 2 this 2.30, so this we can equate with this part, with this right hand side of this equation, putting the values. uh, we get the final equation. M3 is equal to M3 multiplied by 13.819 equals to 2 plus gamma minus 1 into M3 square whole cube. Let us name this equation as equation A, as this would be further used for M3. Now to solve this equation, since uh, as we can clearly see, this M3 would be, if we expand this M3 would be of the order to the power of the order 6. So to cut short the time, we go for heat and trial method or trial and error method. So this, since point 3 in the diagram is a downstream point, now for the first assumption, so as to assume what values for M3 is suitable to start with. Now since point 3 in the diagram is a downstream point, this point 3 is more downstream to point 2. So M3 will be greater than M2. M3 will be greater than M2. Since we know that as Mach number increases, the entropy also increases with respect to it. So we can clearly say that M3 will be greater than M2 regardless of the value of M3. M3 will be greater than M2. That is, M3 is greater than 0.513, which is the value for M2. But since M3 is less than M4, as you can clearly see from the diagram, this point 2 and point 3 are both in sonic conditions. Since this part is subsonic conditions, since this part is considered to be subsonic, so point 2 and point 3 will be in subsonic conditions and will be less than 1. So M3 is less than M4 and therefore M2 less than M3 less than M4. So the first assumption taken from hidden trial method is M3 is equal to 0.6. So putting 0.6 in the equation A, we get left hand side is equal to 8.29 and right hand side is equal to 9.855, and the difference between them is 1.641. And further with assumptions, we put values of M3 0.66, 0.69, 0.699, and you can clearly see the difference. The least difference is this number 0.922, which is for M3 is equal to 0.699. So we see for M3 is equal to 0.699, both the sides of the equation A has the least difference, so it is the most appropriate approximate value. So therefore M2 is equal to 0.513 and M3 is equal to 0.699. Now coming to the final part of the question, which is to find out for F del X by D for the duct. Now for M2, since this constant area part is considered to be the duct, so for M2 we have from table A4 which is the Fanno flow table, by interpolation we get this term for M2 equal to 0.9637. This x star means length of the duct, uh, which would give us sonic condition at the exit of the duct for the respective Mach number. Here Mach number is M2, which is equal to 0.513, which gives us 0.9637. Now for M3 is equal to 0.699. By interpolation we get for this part for M3 we get 0.210815. Now since 4f del x star by d for M2 will is greater than 4f del x star by d for M3, so that means that value for M2 will cross this M3. So if we deduct this part, the extra part from 4f del x star by d for M2, we will get 4f del x star by d for the duct, which we can clearly see from this equation. This gives us 4f del x star by d for the duct equal to 0.753515. And that's all, sir. Thank you for this opportunity. Thank you, sir.